organizers to put together this wonderful meeting that I'm really enjoying a lot, and I'm also putting some weight on too. So as you see, I change gears here, and I go to this non-trivial or not evident title. So I will try to tell you a little bit, like an overview of the things that have been very interesting for me in the past few years. So if I say solid-state neuroscience, I have to, and I work in the solid-state physics lab, I have to explain why I believe that neuroscience belongs in a solid-state physics lab. And let me justify that with an analogy. So in solid-state physics, we are interested in materials, like one particularly important one is iron. And iron is particularly important because it has a functionality which is useful. Magnetism was discovered very early on. But then more recently, we learned how to measure that and make this quantitative. This property is more quantitative. And then we start to have to model it to see if we understand what's going on. And then we write an Ising model, and we solve it in mean field, and we find that this thing resembles the magnetization, and we are happy, and we think that we're interested in the essence of the thing. Then you can improve upon that, but we think that we understand the essence. Now, for neuroscience, the material is like a gray matter, or the brain, or however you want to call it, and it has an obvious functionality. That's why we're here. And this can be measured under different forms, more sophisticated recently. But then we have to model it if we want to understand what's going on in this system. So this is the driver for this, trying to understand what's going on in the brain, how to understand its function. So as a condensed matter physicist, we worry about degrees of freedom, interaction, and networks. In the case of iron that I mentioned before, we look at the iron atom, and we find, oh, OK, it has some 56, I think, electrons and so many protons. And we start wondering, is that important to describe magnetism? And we can argue, yes, no, how about maybe the last electrons in the outer shell under magnetic moment, and blah, blah, blah. And then we also worry, is the lattice important, the FCC, the BCC? What are these things? So these are the things that we normally worry about. But here we are dealing with something different. The brains and the neural systems are, the units are not atoms, are fairly complicated cells. These are cells. Our body is made out of cells. The neurons are a particular type of cell. They still have a body and a nucleus and all these things that we know, but also it has all these ramifications. So it has all the dendrites there, and it has an axon, and it's connected to other neurons. But the most important thing is that these are electrically active. So these are cells that are electrically active, and when they are excited, they emit what is called an action potential. So this is the kind of electric signal. This is time, and this is voltage. This is the electric signal that the neuron emits when it has to convey information from one to the next one. And networks, well, we don't really know much about how networks of neurons are in our brain, but this is a very exciting new area in neuroscience, which is called connectome, because we are learning how to start mapping the neural networks. And this is under rapid development. OK, so if we want to model this, what do we do? Well, we have two options. One is to do algorithms and mathematical descriptions, software, or hardware with computers. And for that, like most of the modeling of neurons follows the route traced by the pioneer work of Hodgkin and Huxley. which received the Nobel Prize for describing how this action potential is generated in a cell. And they did that by means of many differential equations, sets of differential equations. And then people, solve those equations and obtain different behaviors that are related to what is observed in real life. And then you have to argue what kind of network of neurons you're interested in. And then you have to start seeing what is the behavior that you get out of that. And that is a big driver in our artificial intelligence. On the other hand, we have neuromorphic computers, neuromorphic chips, like most notably from IBM, True North, Intel Ohihi, the FPGAs. But all these things actually are dedicated conventional computers to try to solve this kind of problems. So they are well adapted to deal with lattices of neurons that are doing a very simple calculations. But these are just computers to try to solve these algorithms. And all this activity is driven by the wonderful advances in artificial intelligence. But if one really wants to know how neural networks work, one has to solve sets of growing differential equations which have to deal with delta functions. And the time, having done numerical physics for many, many years, I know that the scaling for these things is horrible because you have to deal with delta functions. And when you have more neurons, there are more delta functions. So you worry about the time discretization. And also, you need to evolve the system for longer and longer time, but you need a shorter and shorter discretization. So it really becomes hard mathematically. So the question is there an alternative route to this thing? And the answer is we can make neurons directly in hardware. So the analogy will be the same way we want to solve the Hubbard model by building qubits, and with those qubits, make a quantum computer and fabricate a Hamiltonian. Here we can just build neurons and interconnect the neurons, which are units that behave like we think that neurons behave, and then interconnect them and try to understand the emergent behavior. So for that, we need materials with new neuromorphic functionalities. We need materials that behave like neurons. So that is what I'm going to tell you about. So all this can be done by exploiting a property of materials which go by the name of resistive switching or memristance or memristors. It is the combination of memory and resistors, and the physical phenomenon is a sudden change in the resistance under an applied electric field, so a voltage. And the second point is that there is memory, and then what you observe is hysteresis effects in the IV. So the change in the resistance depends where the system was. So basically you have material, and this has been studied intensively for the past 20 years, an important non-volatile effect. Non-volatile means like semi-permanent, like in your USB key is non-volatile. You can disconnect it, but it keeps your transparencies, your photos, or whatever you want to keep. But you can just change it. You can write it again. So that has been intensively investigated in transition metal oxides. I was also involved for 20 years. But how about a different effect in a mode insulator? So this is a relatively new discovery. It's the volatile effect. It's a sudden resistive change in a mode insulator. It's basically just destroying the mode insulating phase, collapsing the resistance. You know that mode insulators are materials that should have been metallic. If you do the band structure calculation, it should be metallic. But in real life, they turn out to be insulators. So is it possible to destroy that insulated character by applying electric field? And the answer is yes. And the unexpected finding is that this creates a new functionality, a neuromorphic functionality that allows you to fabricate neurons. I'm going to describe that now. So this work started when I was approached by this group from Nantes. These are experimental guys that were investigating this system that people thought it was a Mott insulator, and they were applying electric fields and destroying the Mott property. So being involved in describing Mott insulators for many, many years, I looked into the problem. I was excited about that. They grow beautiful crystals that I sent to my colleagues in Buenos Aires, Carlos Sacha, who did experiments under pressure, and Alberto Kamhashi, that did the DMFT of the system. And it turned out to be a beautiful Mott material. So this is the stoichiometric compound of this system with x equal to 0. And you see how beautiful it is. At room temperature, you have a resistivity. And then all these different curves are for different applied pressures. If you don't apply pressure, this system is a Mott insulator. And you see the activated behavior of the resistivity. As you lower the temperature, it goes up. But then you apply a modest, a relatively modest amount of pressure, like 5 gigapascals, and you see that at room temperature, you don't see any change. But when you go beneath 100 Kelvin, this thing crashes down and becomes a Fermi liquid, and you see more than 10 orders of magnitude difference in the resistivity, which is huge. I don't know, besides astrophysics, who has like 10 orders of magnitude, and this is on a tabletop. And the most beautiful thing is that in DMFT, one of the hallmarks of the Mott transition was this coexistence of solutions, this first-order character. And you see that if you stop in between 3.5 gigapascals, you find hysteresis from an insulator to a metal or a bad metal, and which is the hallmark of that. So this is a wonderful Mott system that I couldn't avoid describing a little bit. So the problem is that we really develop understanding of Mott insulators in equilibrium. But if you apply an electric field and you try to destroy that Mott property, you're pushing the system totally out of equilibrium. And there are a lot of developments in studying the problem of the Mott transition out from equilibrium, but still it remains a technical challenge. So to try to keep up with the experiments, we took a shortcut with Pablo Stoliar, who was a postdoc at the time with me, and we investigated a resistor network. And this resistor network, each unit was informed by the DMFT, the results from DMFT that tells you what are the properties of a resistor and metal. And the answer, I'm not going to go into the details because I don't have a lot of time, but basically the answer to this problem within a resistor network was that the system must form filaments. So it's not that you have a full thermodynamic phase transition, but what you really have is filaments of metal growing inside an insulator, and that is the origin of the avalanche. But you may be thinking, okay, that may be so, but a resistor network, I mean, you may be just tricking us very much. And this, so this is a volatile effect I was mentioning. So you apply a voltage, you monitor the resistance after some delay goes down big time, and then you switch off the voltage, and the system recovers. You see that within 1 millisecond, the resistance already recovered. And you can apply a voltage again, and you do this over and over again, and you get exactly the same experimental points, one on top of the other. So there is no migration of vacancies or defects. It's really the electronic state that is changing, and nothing else. So going back to the validity of this.
Very quick question.
Yes.
The time scale here,
yeah.
in terms of microscopic time, is very large.
Yes.
Is this a collective effect of this large scale, the time scale microscopically, although microscopically it should be much smaller than that?
Yes. The totally honest answer to that is that we don't know. if you do a out of equilibrium study of a Haber model, all the timescales are very, very fast. But for a transition, right? For a homogeneous transition. Here you have to create a filament, and the filament has to grow. So, and there is also evidence of electromechanical phenomena, electroelastic. So that may lower the thing. So, but that is a very important point that needs to be addressed. Also, the electric fields that you need to produce the transition are at least 3 orders of magnitude smaller than what you would naively get out of a Landau-Zener type of transition. So all the, but it's very consistent, many different compounds, so that's pretty solid. Yeah, so that is a valid point. When I say that it's reproducible, it's compared to the other resistive switching that we know, which involves the motion of the effects, ionic motion. So here is essentially reproducible. It may be not perfectly reproducible, it's quite reproducible. So it might be that the filaments grow along some dislocation, defects, or whatever. So, but I've seen their experiments, and you see the points going one on top of the other with a variability which is much, much, much qualitatively different from the volatile effects where you have a motion of ions. So you can think of this as something like elastic, and the other is like plastic, if you want. Like, there are no defects involved. Okay. But then, coming back to the model, I said, how about a non-trivial validation? So, okay, so the key point from DMFT is that you have coexistence of states at the mode transition. That means that the mode insulator is stable, but nearby there is some correlated metallic state nearby in some phase diagram, which should be accessible. So the assumption was that with an electric field, you access that, maybe locally doping or whatever. But when you are in that metallic state, the system has to relax back. So if it has to relax back with some metastability and some barrier, there should be some time, characteristic time, associated for that relaxation. And actually, the whole system relaxes back. So it has to be associated to that time scale. So with our model, we said, OK, let's apply a very short pulse, shorter than the time you need in order to provoke this transition. So if you apply a very short pulse, the system will just change somehow into that metallic state, and the effect, and then it will try to relax back. But if you come with a second pulse, also a short second pulse again, before the total relaxation is done, there should be a cumulative effect. So you accumulate the transition until the system suddenly percolates, and when it percolates, the resistance, the two terminal resistance collapses. So this is our prediction. And then Pablo, who is really an experimentalist, but was doing simulations with me, went to Nantes, did the experiment. And this is the data that he obtained. So the system applies a very short pulse. The system doesn't collapse there, but you start applying pulses, and he did this very systematically and show exactly what we were expecting. So we got really excited about that, but then we have the first aha moment. And the first aha moment was, oh, this thing is like a neuron. Neurons receive pulses, and then they get excited. When this system collapses the resistance, then a spike of current goes through the system. It was an insulator, but then when the resistance collapsed, spike of current goes through the system. So this is what neurons do. So coming back to my neuron, the neuron gets spikes, coming through their dendrites, coming from other neurons that are injecting these currents into the soma, the body, the cell body. It is integrated here, and when this reaches a threshold, then an output spike is coming down the axon. This is the action potential that is communicated to the next neuron. So this thing has been described, modeled, even before all the details were known, more than 100 years ago, in a very simple model, which became a classic model. It's like the icing model for a spiking neuron, which is the leaky integrate and fire model by this French couple more than 100 years ago. So this is the integration coming through all the dendrites. You see, it comes one spike to the neuron, it integrated, so the voltage of the neuron goes up, it starts relaxing, and then another one comes, and before it totally relaxes, it integrates that, and then it relaxes, another one came, and then eventually, when this one comes, the system goes over a threshold, and when it goes over a threshold, it emits a spike. So this is the fire. So this is an integrate, leaky integrate, and then here goes over the threshold, fire. And then when fire comes out, a spike that is communicated to the next neuron. So we got really excited. We were able to put, the systematic pulsing applied to this compound, this mode compound, in close analogy to what you expect from a leaky integrate and fire. And we published it, and eventually we got a patent out of that, and I got very happy as a theorist to have a patent. Very good. And then, since then, things have been really a lot of fun. I got into a collaboration with the group of Ivan Schuler in San Diego, who is perhaps one of the best groups that can do films of mod insulators. Here is a film of VO2 with some electrodes there, so you can apply voltage. Making a film is very good for applications in electronics. And we've been there are very amazing phenomena that I would love to discuss about, but we all understand that with our filaments and the metastability and the transfer of heat and so on and so forth. So this has been a lot of fun, and this is still going on. But, mod insulators can be fabricated, but they are very, very hard to fabricate, to control, to manipulate, to understand. So one may think, how about just conventional electronics? We can do, with modern electronics, we can do everything. So how about it? Just like a spiking thing, of course, can be done in electronics. And of course it can, and there's a lot of work done by electronic engineers, especially the group of Indiveri in Switzerland. So the problem is that, this is the kind of neurons that they fabricate. I don't know how to read about that. And they fabricate it in VLSI, which are like microchips that take many years to develop. And then you can make millions out of that, but you cannot change anything. So from, a model kind of physicist, this thing is an amazing engineering development, but then how you can tinker with that. So I wonder, can't we have the best of both worlds? Like, namely, the simplicity of mod memristors, but the reliability of conventional silicon electronics. And this was the second aha moment, or aha moment. So it was like, memristors can do the trick. So the simplest neuron that you can think of can be described with a memristor very, very simply, which is you put a capacitor to do the integration of the leaky integrate and fire. The memristor is a resistance, which is initially at very high resistance, so you have a leaky integration. But then this capacitor will be charging and charging and charging, and leak charging. But at some point, the memristor will reach a threshold, and when it reaches a threshold, it collapses its resistance. And when it collapses its resistance, the capacitor will just discharge through it, emitting a spike. So you recreate a leaky integrate and fire model. And the second aha moment was to recognize that there is a conventional electronic component, which is called the thyristor, that in combination with a resistor generates a memristor that does the trick. And this was out of recognizing that the IV curve of a thyristor that I Google into the web, there are components that do that, immediately recognize that the IV curve of a thyristor is totally analogous to the IV curve of a mod system that I've been working for many years already. So I said, with a thyristor, we can make it happen. And with Olivier and Pablo, we sat down and we discovered that this very simple circuit does the trick. So here you have a capacitor that does the integration, the resistance does the leak, and the thyristor does the fire. The thyristor is just a diode with a threshold. So you put it in direct, but it doesn't conduct immediately like a normal diode. It goes with high resistance until you reach a threshold, and then it starts conducting. And the mod does the same. It's an insulator, you reach a threshold, and it starts conducting. And when you switch it off, it comes back, so it's volatile. To make this more precise, this is a recent paper with a group of Schuller, where you see V305. This is one of the mod materials that they like to fabricate. This is the IV curve, where you recognize this shape. There is some hysteresis there, and this is a memristor made with this thyristor plus resistor, and you see that qualitatively looks the same. Voltage, high resistance, low resistance, hysteresis there, and with this thing you can generate spikes like that, and with this you can generate spikes like this. The problem here is that to do this mod, you need to learn about film deposition, develop a know-how of more than 10 years, and have lithography equipment, and sputtering, PLD, whatever thyristors are available online for next day delivery. It costs literally pennies all over the world, and they always work. And the only problem you have is that if you grill them, you have to get your student to throw it away immediately, because if they get mixed up with the good ones, then you go nuts. You have to throw everything and start from scratch. But you can buy it by the hundreds. So these neurons cost nothing. They work at room temperature. You don't need low pressure. You don't need vacuum. You don't need nothing. It's just conventional electronics. So with these neurons, we started building circuits, and we made a very fast progress in the past few years. So I don't know if I'll have the time now to tell you about the recent works that we've done, but this is just to emphasize that we have, how many minutes we have?
10 minutes.
10 minutes. Okay. So these are just like two particular works that we have done. This was just a classic model. It's called the Jeffers model. It's a classic model from neuroscience, where it allows you to detect from which direction you've been talked to. So basically, you're in the center, and a spike sound arrives to your left ear and to your right ear, and then you have a delay line. Maybe I should put the next transparency. So this has been found in the brain, explicitly in the brain of birds, chickens, I think, but we believe that maybe also we have that kind of thing. The model is from the 40s, so it's a classic model of neuroscience. So when sound arrives to one ear, say the left ear, it starts emitting a spike into your brain, and from the right ear, you get a spike into your brain. They go through delay lines. So if those sounds arrive to both ears at the same time, and they start traveling this way and traveling this way, they will coincide, they will cross in the middle. So this neuron will get two spikes at the same time. It will detect the coincidence, and then this one will tell you you've been talked to from the front. If you're talked from say, the left, then the left immediately this will arrive faster than this, so this arrives and starts traveling, and then the right ear starts traveling later, so you're going to have a coincidence somewhere over there. So we took this model and we implemented with our neurons just to show that we can associate neurons. It's not, you can imagine that with mod materials, still the fabrication of neurons is at the single neuron state. We're trying to control one. So the question of associating more into a functional circuit is still way ahead. So having these electronic neurons, which are simple, allows you just to build like Lego blocks. They're all the same, and you fabricate that, and this is the data that we obtain, and we got this accomplished. Another example is very important in neural networks is the phenomenon of recurrency. The recurrent neural networks are supposed to be good to analyze speech, for instance. So, and of course, they are very challenging because you have a feedback you have loops of feedback all over the place, and with spikes, that's very hard to understand. As a physicist, I thought that, well, the minimal one would be just to put one and to take the output and feed it back into the input. And I thought this problem has to be beaten to death. Well, it was not the case. This has a name. It's called the outtaps, and it's considered an aberration for neuroscientists. They assume that they are not there, but apparently it's not the case. There's very little work done on that. So some models are available, and I can tell you the details, but we show that we can have this greater persistent activity, which is important for your eye. It's the oculomotor system. So if you want to keep your head straight but look that way, you have to look that way with the muscles of your eye, and you have to keep your muscles there, and then you have to relax them. So to keep the muscles there, you have to fire more. So this you can do, and we basically qualitatively got the same things. And the interesting thing is that if you read the paper from very well-known neuroscientists, this is so hard to model that they really worried about the stability of that, and you read through the paper, and it's very complicated, and they're not really sure that the system is stable. But here, we just fabricated it. So there are no issues about stability. It works. So by fabricating something, you demonstrate immediately, without any questions, that the system works. So that's, well, and we also, for instance, this is, Can you?
You said the neuroscientists say that
Yeah.
is obsolete.
There are aberrations. But then a recent paper, Nature Communications, a few years ago, you find this paper, for instance, when they observe the autopsies, they map the dendrites and the axon and so on, and they claim they are not rare. 30% of the neurons in layer 5 are autopsies in epileptic humans. So epilepsy may be related to this thing because a feedback just like overexcites the neuron. And they did some experiments with voltage clamp. I mean, the paper is very long. I just took some experiments that I could go through them. And we use our system to try to fit that. So with our system, these are our experiments. This is all experimental data. And this is data from the paper, and we were fitting experimental neuroscience data with our system, which made me, very, very happy. So this is just like a demonstration, the contact that we can do with our system. The most recent work that I want to briefly mention is, here you can recognize the simple leaky integrate amplifier. But in models of neuroscience, you know that and this thing only just like spikes. But neurons do different kind of things. And if you want to understand Parkinson's disease or epilepsy, they go into bursting or anomalous bursting. So bursting is an important feature of neurons also for motor motion. Like if you want to command a muscle, it's better to command it with a burst rather than to a spike. It's more reliable, so bursting is important. And in all models, you need to add a second time scale. In our circuit, it's very easy. We add a second time scale by an RC circuit with a time constant tau, which is just the product of R and C. The classic model from neuroscience of bursting is a two-compartment model where you have explicit dendrite, explicit soma, and you have a bunch of differential equations. There are many, many, many more with lots of parameters, and this is just for one. So you imagine if you want to make a circuit out of that, you're in really trouble. If you want to understand the global behavior of that, and you have all this to deal with all these very nonlinear differential equations, you're in trouble. So we did this. We started playing with the parameter of the time scale, and we observed these 4 qualitative different spiking forms, where this is the tonic one, which is the simple spiking that we had. We have a second one, which is fast spiking, and then we had 2 types of bursting. So we went to the literature, and we found, this type of bursting is there, and we found this experiment. And then by changing the value of I think the current there, we moved from here to here, and then they moved from there to there, applying neurotoxins. And this is another example with other types of neurotoxins of these bursting neurons. And you see that you have spikes, you have fast spiking, and then you have bursts of the very qualitative, nice behavior. But since we do solid state, we look at this as physicists. So I said, OK, what about the phase diagram? I want to have a global view of this. So this is applying current. If you just have a spiking system, we just have here tonic spiking with the spikes. But then these are the phase diagram as a function of this second parameter, tau, this RC constant. We fix the C, and we change the R with the potentiometer. It's very simple. And we map the whole thing, and we observe different qualitative different behaviors with.
What is tau S?
What is? Tau S is the time constant, the RC times constant of this second block. So if R goes to 0, you short circuit this and you go back to the original circuit, right? And then you fix C, and you can change R and have different behaviors. So here, this limit, tau going to 0, is R going to 0. So this would be like the simple spiking behavior, leaky, integrate, and fire. And then you put the second parameter, and you get out all these phase diagrams. And then you can really start getting exciting things, like, for instance, finding an experiment where they take one of these neurons, pacemaker neurons, which are key for all the sequences in your body, like generating, the cardiac or respiratory. Well, I mean, I'm not the person to ask, but you have these pacemaker neurons, which by applying a neurotoxin, you can just make them quiet. So here it doesn't work. And then you start exciting it by applying current to that, and you see that it starts burst, and then it bursts more, and it bursts more, and then it becomes fast spiking. So then you're tempted to think that they may be in this region of the phase diagram, where you start with a quiescent, that is a neuron that doesn't work, and then you apply current. So we move vertically, as they do in the experiment, just increasing current, and you go through increased bursting and more bursting, and then you end up there with fast spiking. And this is just one experiment, one example of many others that we have. So just to finish, I want to tell you some personal thing. So a year ago, I fell victim of the theoretical physics middle life crisis. But I didn't buy myself a red convertible. I bought myself a lab and started a new life as an experimentalist. So now as an experimentalist, as you all experimental guys do, you're allowed to show your equipment. So this is my equipment. It's just an electronic lab where you can see oscilloscopes and these are my students. So this was 1 year ago, and we were very excited doing experiments there. And I hope I convince you that it's worth, that really this neuroscience belongs to a solid-state lab. And if you are not satisfied with my arguments, I leave you with Feynman. So Richard Feynman, when he passed away, they took a picture of his blackboard. And in the top of the blackboard, you see that he had written for himself, what I cannot create, I do not understand. So when I saw that, I said, oh, that's how I feel. So I want to create the neurons to understand them. So thank you very much.
That was a very nice, interesting talk. So are there some questions? Well, I think everybody agrees that it was a wonderful talk. Marcelo, going back to the bursting thing, I just have a question. I don't know if I'm way off mark here, but I understand that the neuroscientists, they had this model there. It was kind of complicated, the bursting thing.
Yeah.
Can you go back to the... Yeah.
Yeah.
So you had this thing over there, right? Which the two-compartment Pinsky-Rinzel model.
Yes.
So if I understand it correctly, that is modeled by those differential equations, horrible differential equations. Is that right?
That's right. Yeah, these are equations taken from that paper.
Right. And if I understand you, you basically simulated that with, I don't know, 4 elements like that, right? Of which one of them is nonlinear, which is the memristor, and everything else is linear. So this looks to me like lump components in a lab, right? If you take 5 resistors, you connect them, you get an equivalent resistor, and you can build circuits with linear components, you can have nonlinear components, and so on. So I wonder if there is a sort of a universal neural circuit approach where you have, I don't know, 5, 4 basic components, and you can build any circuit, any neural circuit you might imagine. Because I think that's what was done here, right? Am I correct in saying that?
Yeah, well, there is a very influential paper by a mathematician, Russian mathematician, that it's called like 20 biologically relevant behaviors. So he wrote a mathematical model with very few parameters, not biologically inspired, because he was a mathematician, and he knew like what kind of dynamical phenomena you can get. This is a glorified periodic system, so a glorified pendulum. So he knew what kind of parameters add to his basic differential equations in order to generate all different type of behaviors. And he found out that by tuning, I believe it was just like 5 constants out of his 2 differential equations, he could get the 20 biologically relevant behaviors. And it's a beautiful paper. So that was our first thing. So there you have. This is not biologically inspired. It's different from Hodgkin-Huxley, which they model the channel of calcium, the channel of potassium, and all that. So we thought, OK, we're doing something like Ishikevich, but in electronics, in hardware. So we have our very simple system with very few tuning parameters. And let's see what we have to add in order to get the 20 different behaviors. And we got like 12 tinkering very easily. You add a filter here, you add it there, you put a feedback here. And we have a paper, I didn't mention it, but our first paper was 12 biologically relevant behaviors, and we got many, many different things.
Wonderful.
But I really like the bursting one came after. We couldn't get bursting before. And that was just one student, by mistake, a serendipity, that he put this resistor too big from what we were putting, and then suddenly he got like all these oscillations, and I said, oh my God, that's for bursting. So it's very, yeah.
And that memristor can be replaced by a thyristor.
This memristor is
a
thyristor with a resistor. So it's just this. It's just, yeah.
Okay.
This circuit is that circuit. And then we add just an RC beneath this guy, we just put an RC. But it's just a thyristor and a resistor, and nothing else.
Very good. Thank you.
Hi, Marcelo. Thank you for the nice talk. So at the phase diagram, when the current is too high, you return to the quiet limit. Can you explain why?
Yes.
I couldn't understand.
Yes. By the way, neurons, real neurons, do that too. In a leaky integrated amplifier, it doesn't, because you just keep on increasing the current, and it will spike faster and faster. But in this system, it does. And the reason it does is that, you see, you have an IV curve like that, or I can just put the real one, the measured one, there. So if you're injecting current that is above this, it's called the holding current. If your injecting current is above this value, then you will, of course, go into this branch. The capacitor charges, then the resistance collapses, and the system is there, and it starts discharging. But if you're injecting continuously current, which is too high, the system will remain in the high resistance state, and it will be shorting. So
Okay, thank you.
More questions?
And presumably in real neurons, that thing can happen too. If you use overexcited neuron, it becomes hyperpolarized or underpolarized. I'm not the person to manage all these things, but the neuron stops responding. So they have a range of frequency that they span, which is about a factor of 5 in frequency, and that's exactly what we observe with our system. So by the way, you can just like very easily tune these neurons to work on biological timescales, because 1 microfarad and 1 kilo ohm will give you 1 millisecond, which is the time scale of real. So we're there. And of course, we can build circuits that are much faster than biological ones. That may be useful too, but we can span a big time scale.
I have a question which is actually a curiosity. So about synchronicity. So is there a way to implement synchronicity of synapses in your solid state model of neurons?
Yeah, that's a great question, and is the kind of direction that I want to move on. I already achieved 1 neuron. It's been a lot of fun to obtain this bursting and understanding this. But really, I think the hard problems are understanding what are the mechanisms of large networks. And we want to start like microscopically, associating few neurons and see what. So in oscillatory systems, the problem of synchronicity, it's been widely investigated for periodic systems. Now, in this case, we have 2 ways of interconnecting the neurons. So one is via capacitors. We started already with that. And you observe that they become synchronous, and so there are many emerging states out of that. This is totally to be explored. More realistic regarding neural networks is not capacitors, because as far as I know, and I've been asking around, neurons are not capacitively coupled. I really wonder why they cannot be. I think they may. But in any case, they believe that they just inject currents to others, and the currents can be positive or negative because they can excite excitatory neurons, excitatory synapses, or inhibitory synapses. And this is, in this system, it corresponds to injecting positive current or drawing a negative current out of it. So this is the direction we want to go, start associating, trying to keep well-known models, like this Jeffers model, just to follow that. We are now implementing learning, which is an important feature. So we're now like a kid in a candy store. We don't know what to grab first. It's really exciting. And there is plenty of work. Anybody interested, I'll be happy to share these circuits with you, and you can just set up a lab at your place and have the fun that I'm having.
Okay, so I'm sure there are many questions still, but we are running late. So we can continue over coffee. So let's thank Marcelo again for this nice talk.